Hello, and welcome back to the Maths Behind the Economics YouTube channel. We are still continuing with the Logarithms for Economics series, and in this video, which is video 8, and I'm going to show why and how the multiplication behind the log sign rule works. So first of all, I'm going to introduce you the rule again. Then I'm going to explain to you why the rule works, and as always, we are going to look at plenty of examples. Let us get started. I spared you the pain of having to watch me writing this out in my handwriting, so we can all see it nicely and neatly how the rule works. So, if I have got any log base, which I can just represent by b, and if I have some multiplication of quantities behind that log sign, then I can break that log into two separate logarithms with an addition between them, but importantly, the logs have got the same base as the original log, and the arguments are now separated into individual arguments. In the original expression, we had got a multiplication of two different quantities behind the argument. Now, on the other side of the rule, we have got individual arguments behind each of those log signs. And as always, because economics students work with the natural logarithm ln very often, I like to present the special case of the rule with the e-based logarithm ln as well. So if I have got ln x times y, that's going to be equal to ln x plus ln y. Now, let's start to have some feeling to see whether it works or not. So, if you think about log base 3 times 9, I'm going to put that into a bracket so we know that the log applies to both of the multiplication. Should that be equal to log base 3 plus log base 3 9? Is this true? Let's see if we can convince ourselves. Now, what do I know about log base 3 times 9? Well, I can do the multiplication behind the log sign inside the bracket. So I can replace that with log base 3 times 9, which is 27. And now, if you remember from video 1, we can replace log base 327 with 3, because 3 raised to the third power is going to give me 27. 3 times 3 times 3. Right, so the left-hand side of the equality, or if this rule, the log base 3 times 9 is equal to 3. So I can write a 3 into here. Let's investigate what happens on the right-hand side. So on the right-hand side, I have log base 3, which is just equal to 1 because 3 to the first power is equal to 3. And I have to add to this log base 3, 9, which is equal to 2, again because 3 squared is equal to 9. So if I look at these two, which I'm going to have to add together, that nicely and neatly adds up to 3. So the right-hand side of this rule or equality is also equal to 3. This is nice and lovely, but this is just one example. Remember, examples are not proofs. So first of all, let's check if this stands with a slightly different example as well. Let us make a bit more space and see if this rule holds for log base 2 4 times 8. Is that equal to log base 2 4 plus log base 2 8? Follow through with the same logic. The left-hand side, I'm going to use LHS for this left-hand side, is log base 2 4 times 8. Now, what is that equal to? I can multiply 4 and 8 together. That's going to give me 32 because 4 is like doubling and doubling again. So double of 8 is 16 and the double of 16 is 32. But I also remember that 2 to the 5th is equal to 32. So this whole logarithmic expression is equal to 5. Remember, log is the exponent. It's the power to which I need to raise the base, so I get the argument. So that's the left-hand side. Let's look at the right-hand side. On the right-hand side, I have got a sum of log base 2 4 and log base 2 8. Now I know that 2 squared gives me 4, which means that log base 2 4 have to be equal to 2. But I also know that 2 cubed is equal to 8, so that means that log base 2 8 is equal to 3. Now remember, the logs are the exponents, the powers. That's the way that we created this concept in the first place. Now, the right-hand side is actually the sum of these two, so that has to be equal to 5. Again, it nicely ties up because log base 2 4 times 8, which is the left-hand side, is equal to 5, and at the same time, log base 2 4 add log base 2 8 also adds up to nicely 5. Now, I hope I have convinced you with these two examples that this rule actually works. But two examples are no proof for anything. What if it doesn't work for, let's say, log base 7 or something other? So we need to have a form of proof. And as an economist, especially in the dawn of artificial intelligence and large language models, you really need to be on top of your game, and you have to be able to think logically and be able to convince others that whatever you do is the correct way of thinking about and working with something. So I strongly believe that by showing you the mathematical proofs and the mathematical logical thinking, I'll enable you to be successful in these turbulent, ever-changing days. So let's go and investigate why should this work in all log bases and with all arguments. For that, first of all, I'm going to need more space. So remember, in previous videos we had to establish that the base of the logarithm have to be positive, so it can't be 0 and it can't be negative, but also the base cannot be equal to 1. So let's remember this restriction and use the proper mathematical way of writing these down. So let b be positive, but also not equal to 1. And also remember that the argument had to be positive as well. So then also make the restrictions on the arguments, which we were going to use x and y for, that is also positive, both cases. So remember in video 6, when we talked about some special logs, that we could define that b to the log base b xy is just equal to xy, where xy is x times y. But using the same logic, I can also state that b log bx is equal to x, and b to the log by is just equal to y. But this looks a little bit strange if you haven't seen video 6. If you stop and think about it, it's kind of clear, because remember the whole point of the logarithm that it is the exponent. So when we introduced the logarithm, we were asking ourselves the question, what is the exponent that I need to raise some base to, so I end up with the argument or the answer? So this is just formally rewriting it using the language of mathematics. Now, why is it good for us? Well, it's good for us because now we have got two ways of expressing x times y. I can write x times y as b to the log base b xy, but I can also write x times y as x times y, and I can replace x by b to the log bx times y, which is b to the log by. Now, if you have been here for long enough and you watch the exponent series, then you remember that in the second video in those exponent series, we showed and explained and proved that if you have got the same bases multiplied together, we can just keep the base and add the exponents together. So let us just do that. Therefore, we can replace this with log bx plus log by. But x times y have to be equal to x times y. Therefore, this have to be equal to this. So, how can we write this down using the formal mathematics? Once we have got a bit more space, we can use the word therefore, very commonly used in formal proofs. B to the log base bxy equals b to the log base bx plus log base by. Now, we need one more step because this is not quite what we wanted to prove. What we wanted to prove is what's in the exponents are equal. not just the exponential expressions being equal. Thankfully for us, we can claim that due to the properties of the exponential function, and here I'm being a little bit sly because I have not introduced you to these specific properties like continuity and monotonity, so I'm not going to claim those, but those are actually the properties that I can apply here, combined with the fact that b itself is positive and not equal to 1, so these properties will hold. We can claim that if the two sides of this equality are equal and same bases, therefore the exponents themselves have to be equal, so then we are safe to claim that log base b xy equals log base bx plus log base by. Now, if you feel like you're a little bit cheated because I just glossed over these important properties of continuity and monotonity, then rest assured that it is in my intention to go over those in later videos. But for now, let us move on to some practice questions. And again, let us make more space. Let's start with question 1, which is log base 10 300. Now you can ask me the question, why on earth would I be bothered applying any kind of rule in here when I can just simply put it into the calculator? And you're absolutely right. You can always just put it in the calculator and get the right answer. But just bear with me and let me show you why and how I could apply the rule here, just in case you might end up in a situation like an exam, when you may not be able to use the calculator, but you need to play around with the logs so you can make something a little bit simpler. So what I can do here is, I know that the base is 10, and I know that 300 is 3 times 100. So let's write down log base 10, 3 times 100, where 100 is a power or exponent of 10. So then I can replace this as log base 10 3 plus log base 10 100, and I know that this log base 10 100 is 2. So this whole expression cancels down to 2 plus log base 10 3. And obviously log base 10 3 has to be less than 1 because 10 to the first power is equal to 10. So I would expect my answer to be 2 point something, but probably less than 2.5. This could be quite useful if you needed to sort of approximate something, or as I said, if you're just manipulating with some quantities which are not quite numbers, but you've just worked with generic bases and you've got an expression there which is 2 multiples of numbers or something. So I still think that knowing this trick could help you out in certain situations. Let's look at the second example, in which we have got a general base b, and I have got 3b here. Oh, what a surprise! Isn't this looks just exactly like the previous example? Well, not quite, but very similar. So I can straight away use this trick. I can replace this with log b3 plus log bb. And I know that log bb is equal to 1. So this whole expression is just going to cancel down to 1 plus log b3. Now, I cannot really give you a kind of estimate of what's happening in here because I don't know whether b is a base that is bigger than or smaller than 3. So I don't know whether this number is going to be bigger than or less than 1. But in this case, I have a somewhat more meaningful result because now I have been able to bring out a whole 1 from the expression, which is probably useful for me somewhere further down the line. So let's look at the next example, and it wouldn't be an example without a natural logarithm example. So let's look at ln 5e. Well, this is going to be equal to ln of 5 plus ln of e. And remember, ln of e is always equal to 1. So this is again just going to be 1 plus ln of 5. However, unlike in the previous example, where the base was not known, I could not calculate log b of 3. I know the base here, which is e, so I can just put this value into the calculator. Well, as a matter of fact, I could have just put the whole expression into the calculator with ln 5e as well and calculate it straight away. But sometimes when you are going through some economical proofs, you might just want to bring out the 1 from here and then work with that further on. Right, let's look at the next example, example 4. This is going to be log base 3 9x. what I can do here? Well, I can break this out into log base 3, 9 plus log base 3x. Well, log base 3, 9 is just equal to 2. So that's going to be 2 plus log base 3x. And the problem here is I don't know what x is. I don't know the argument in the log, so I can't calculate the exact value of this expression, but I know that this will be 2 plus something. And after making a little bit more space, we can move on to our last example for the video, example 5, and that's going to be log base 2 8p squared. So what I can do here? Well, I can break this into log base 2 8 plus log base 2 p squared. Well, log base 2 8 is just equal to 3 because 2 cubed is 8. So that's going to be 3 plus log base 2 p squared. Now, what do I know about p squared? Well, p squared is just p times p. So I can actually apply this log rule again, and I can replace the log base 2p squared by log base 2p plus log base 2p. Now, I don't know what the value of log base 2p is because I don't know the value of p. I don't know what the argument is. But what I notice here is that I have got some quantity, I don't know what that is, but it's some quantity, plus that same quantity once more, and I'm adding them together, so I'm going to end up with having that same quantity twice. So this is actually equal to 3 plus 2 times log base 2p. Isn't that nice and easy? Alright, so thank you very much for watching this video. I hope you have learned something new. I hope you understand now why this rule works, and with some practice, I hope you will be able to prove it should you ever need to. Or if you don't have to formally prove it, at least you start to have some understanding of how formal proofs work, and you will be able to apply them in your economic studies. See you in the next video, where we will be looking at the next rule, which is all about what happens when you have division behind the log sign. Bye!